Jai Hind to all. Today I am here to present the video lecture on subject signal system BEC 403, and this is my fifth lecture, and the topic of this lecture is inverse jet transform. So in my previous lecture I have discussed about the jet transform and its properties, and now it is inverse jet transform, and I am Dr. Amit Garg, Associate Professor in EC Department of Akgec GEC. Okay, so let us start with inverse jet transform. So now if we will see the definition of inverse jet transform can be written like means we are having jet transformed value and we have to find out the sequence, and you know in case of jet transform we are taking the transform of the discrete time sequences. Okay, so the inverse, when you will calculate the inverse, then we will find out the sequence xn from the xz. Now we have given xz and we have to find out xn. Okay, so this xn can be obtained by closed integral 1 upon 2 pi j closed integral xz into z to the power n minus 1 into dz. So this is the integration formula by which we can obtain the sequence xn. Okay, but generally we don't use this formula because the calculation in this particular formula is difficult. Okay, and we are having another methods by which we can easily find out the jet transform, by which we can easily find out the inverse jet transform of any jet transform value, or we will find out the sequence xn. So there are three methods that are used for the evaluation of inverse jet transform. So first method is contour integration method. It is also called residue method, and this contour integration method or residue method is mainly focused or calculated by using this expression. Okay, so there is a procedure by which we can obtain the sequence xn from the transformed value. Okay, another one is long division method. It is also called power series expansion method. So it is another method. We can easily find out the inverse of any this transformed value, or we will easily find out the sequence xn using this method. But the one issue with this method is, while using this method we are not getting the closed form solution, means we are not getting the general expression. If we have to find out the if we have to find out some of the samples of the given sequence xn, then we will prefer this method. And another disadvantage is that we will only obtain one sided solution. So either we will get the right sided solution or the left sided solution with the help of this long division method. Or third is the partial fraction expansion method. So this is the generalized method and a very effective method, and with the help of this method we can find out the general expression also. Okay, so if we are having the general expression for sequence xn, then with the then easily we can find out the sequence xn. Okay, or we can find out the sequence xn for any n value. Okay, and so let us start first with this long division method. Okay, so first we will discuss with the long division method. Before that I am just showing you that how we will calculate the sequence xn with the help of contour integration method. Okay, so first example is based on contour integration method. So here I am just showing you that how we will solve it. Okay, and I am not going deep in the technique. Okay, so we have given the jet transform xz equals to 1 upon z minus 0.25 into z minus 0.5 using contour integration method or residue method, where ROC is given as mod z is greater than 0.5. You know the importance of inverse transform in case of ROC. So if ROC is not specified, then the inverse is not having a unique solution. Okay, means if ROC is changed, then we will get the different results. Okay, we will get the different sequence xn. It means it is possible that for two different sequences we are having same jet transform. Okay, so for uniqueness of ROC is specified. Okay, so as per this method, let x naught z is given to you, and let x naught z you will find xz is given to you. So we will calculate the xz into z to the power n minus 1. Okay, So we will multiply this sequence by z to the power n minus 1 to obtain z to the power minus 1 upon z minus 0.5 into z minus 0.5. Okay. Okay, we can write this in form of x naught z equals to z to the power n, and we will take z to the power minus 1 in denominator, so it will become z. So we are having x naught z, which is z to the power n upon z into z minus 0.5 into z minus 0.25. Okay. So we can see the poles of x naught z are nothing but z equals to 0, z equals to 0.25 and z equals to 0.5. Okay. So now, as per the residue method or residue theorem, we will find out the residues corresponding to each of these poles. Okay. It means the sequence xn is nothing but the residues due to all these three poles. So residue of x naught z due to pole z equals to 0, residue of x naught z due to pole z equals to 0.25, and residue of x naught z at pole z equals to 0.5. Okay. Then we will write it. So residue z equals to 0.5. So x naught z, we will put the value of x naught z in each of this expression. Now we will find out residues. So first residue for pole z equals to 0, this can be calculated. Residue at z equals to 0, x naught z will nothing but z times x naught z, z times x naught z. We will multiply by z minus 0. This is actually, this z is nothing but z minus 0, because the pole at z equals to 0. So we will calculate z x naught z at z equals to 0. Okay. So by this with the help of, and then we will put z equals to 0 in this expression. Okay. So we will get the value 0. So residue at z equals to 0 is 0, and this is the formula for finding out the residue. Residue for a pole of order m at z equals to alpha, where alpha is the pole, we can find out using this expression. Okay. Then we will find out residue at z equals to 0.25. So another pole is at z equals to 0.25. So residue at z equals to 0.25 can be calculated by z minus pole value into x naught z, and then we will calculate the value of residue at z equals to 0.25. Okay. So this, after solving, we are getting this as minus 16 into 1 by 4 to the power n. You can easily solve this. Okay. And similarly for we will calculate for the pole at z equals to 0.5, we will calculate the residue, and here in this case it will become z minus 0.5 into x naught z, and then we will solve it, and we are getting the value. Okay. So we are having three residue values corresponding to these three poles at z equals to 0, z equals to 0.25 and z equals to 0.5, and the values obtained are 0, minus 16 into 1 by 4 to the power n, and 8 into 1 by 2 to the power n. So when we will combine all these residues due to these three poles, we are having the expression 8 into 1 by 2 to the power n minus 16 into 1 by 4 to the power n un. Okay. So this is how we will calculate the sequence xn. So you can see this xn is of generalized form. Okay. And you can also obtain the closed form solution. Now come to the another method, which is power series expansion method or long division method. Okay. So as per this power series expansion, xz can be written as xz, as per the definition of z transform, xz can be written as xz equals to summation n equals to minus infinity to infinity xn into z to the power minus n. Now we will put the values from minus infinity, some of the n values around 0, n equals to 0. So we have taken the values at n equals to minus 2 to 2, and another values you can see these values are coming from minus infinity, and we are having these values up to infinity. Okay. So given a z transform xz with its corresponding ROC, we can express xz as a power series in z to the power minus 1 or z of the form defined in above equation. Okay. So basically what happened, the xz, if we are having xz in this form, then the values of the signal xn are given by the coefficient associated with z to the power minus n. Means these are some coefficient values. Okay, these are nothing but the samples of xn. So this inversion method is suitable to signals that are one sided, that is discrete time signals with ROCs of the form mod z is greater than a or mod z is less than a. However, long division may not lead to a closed form expression for xn. Okay, so these are basically the, you can say, the disadvantages. Okay, these are the disadvantages of this method, means limitation of this method. You can say you can only find out this solution for either for right sided or for left sided signal. Okay, however, long division, another thing is that it may not lead to a closed form expression. Okay, it means you are not getting some generalized expression from this. So now we can see the problem using long division method, determine the inverse Z transform. Okay, so we are taking one expression and we will find out basically the inverse Z transform in two cases. First case when ROC mod Z is greater than 1, and another case is when ROC mod Z is less than 1 by 2. So first of all, the case is mod Z is greater than mod A. It means ROC mod Z is greater than 1, that is exterior to the circle, that is the causal signals. So whenever causal signals are there, so we require for, if you will see here, if we are having in causal signal, so we are getting the expression like this, means we are having in our solution, we are having only powers of Z to the power minus 1. So what we will do, basically for obtaining causal solution, we require powers of Z to the power minus 1. So from this expression we have to find out, and we have to divide in such a manner so that at the output we are getting the powers of Z to the power minus 1. So we will get the causal signal. Okay. So what we will do, basically this is the denominator, 1 minus 3 by 2 Z to the power minus 1 plus 1 by 2 Z to the power minus 2, and numerator is 1. So what we will do, we will write the result in such a manner so that we are having the negative powers of Z. Okay. So we will divide it, 1 is divided by this expression. So if it is divided by this expression, so first we are writing the value as 1. Okay. So 1, so here 1 minus 3 by 2 Z to the power minus plus 1 by 2 Z to the power minus 2. Now we will subtract it, so this will become cancelled out and the sign of these elements will be changed. So we are having next value 3 by 2 Z to the power minus 1 minus 1 by 2 Z to the power minus 2. Now we will put some value here, so that we are having the value 3 by 2 Z to the power minus 1, so that when we will subtract it, it will become 0. Okay. So what we will do, we will multiply by 3 by 2 Z to the power minus 1. We will write 3 by 2 Z to the power minus over here. So when we will multiply it, so we are having values 3 by 2 Z to the power minus 1 minus 9 by 4 Z to the power minus 2 plus 3 by 4 Z to the power minus 3. Again we will solve it. And similarly again values, we are having the power of Z to the power minus 2. So 7 by 4 Z to the power minus 2 minus 21 by 8 Z to the power minus 3 plus 7 by 8 Z to the power minus 4. Then we will again subtract it. So when we will subtract it, we are having this value. Again we are writing this value, and this process will be continued. So this is up to us that how many values of xn we want, how many samples of xn we want in our solution. If we want more solution, then we have to do it at a we have to again divide it. Okay. So the final value of xz that we are getting is 1 plus 3 by 2 Z to the power minus 1 plus 7 by 4 Z to the power minus 2 plus 15 by 8 Z to the power minus 3 plus 13 by 16 Z to the power minus 4 plus up to 12. So now this is nothing but, if you will compare it with the standard expression, then you will find this is nothing but the value of, this is x0, this is x1, this is x2, this is x3, and this is x4. So you can write it like this, and this expression will goes up to infinity, or till then it will not be cancelled. Okay. So you are having this is the value. Okay. Now another thing is that now ROC is given as mod Z is less than 1 by 2, that is interior to circle, that is anti-causal signal. So it requires power of Z. So in case of anti-causal solution, you can see we require this solution. Our solution will consist of this only. So you can see here the powers of Z are positive. We are not having negative Z powers. Okay. So that's why we will divide in such a manner so that after dividation we are having the positive powers of Z. Okay. So here how we will write it? So 1 is the numerator and denominator is this 1 minus 3 by 2 z to the power minus 1 plus 1 by 2 z to the power minus 2. So for getting positive powers of z, we will write this expression from here to here. So it means like this. Okay. Now our aim is to cancel out this value. Okay. Our aim is to cancel out this value. We have to cancel out this value. Okay. So for cancel out this value, you have to choose a value in such a manner so that multiplication of this and this will become 1. So first value will become 2z square, because when you will choose 2z square, you are having one value over here. Then you will again subtract it. After subtraction, you are having this value. Now our aim is that you will choose this value in such a manner so that this will become 3z. So we are having value 6z cube over here. Okay. So we will target this value only. Okay. So similarly, we are having in next stage 7z square minus 6z cube. Again, we will put 14z to the power 4. In next stage, we will put 30z to the power 5 and up to so on. And again, you will do this in such a manner so that you will get the positive powers of z. Okay. So this is the value of xz. You can see this is the value of xz. Okay. Now we will write the solution, and you know the solution here is left sided. So you can say at right side you are having the values corresponding to n equals to 0. So if you will compare it, this value is correspond to x of minus 2. This is x of minus 3. This is x of minus 4, and the value corresponding to x0 and x of minus 1. These values are not coming here because the corresponding z values like z and z to the power 0 are not here. So these values are 0. So that's why while writing this expression or the output 0 0, and then the value comes to 6, 14, 30, 62 like this. Okay, and up to so on minus infinity. Okay. So if we will again divide it, then we are having some another sample. So you can see from long division expansion method, we are having some selective samples. Around generally values we are getting around 0. Okay. So if we needed some samples of the input signal, then we can choose this method, and if we solution in one direction is required, then we can use this. Okay. Now the generalized method, which is partial fraction expansion method. Okay. So in analyzing discrete time systems, we usually more interested in finding a general expression for the discrete time signal corresponding to a rational jet transform, rather than in finding just the few samples by power series expansion. Okay. So generally we are interested in finding general expression rather than expression for one-sided or one-sided solution. We are interested in general solution, means for any sample, for any n value we will get the input value. Okay. So to find the general expression, we can use partial fraction expansion and the known inverse jet transform pairs of low degree rational functions. Okay. So now we will see one problem based on this. So using partial fraction expansion method, determine the inverse jet transform. So that will become xz equals to 3z to the power minus 1 upon 1 minus z to the power minus 1 upon 1 minus 2z to the power minus 1. Okay, so we have to find out the inverse jet transform in 3 cases where the ROC is mod z greater than 2, mod z less than 1 and mod z is lying between 1 and 2. So first case, first of all what we will see this expression xz equals to this. Then we will write it in positive powers of z, so that by seeing this we can see that number of poles are at z equals to 1 and z equals to 2. So there are 2 poles. Okay. So if we will see the first case, okay, let me complete first. Xz by z, you can write it like this, and then we have done the partial fraction, and after partial fraction we are getting the value of xz equals to minus 3 times z upon z minus 1 plus 3 times z upon z minus 2. Okay. So we are having this value of xz, which is minus 3, 1 upon 1 minus z to the power minus 1 plus 3 into 1 upon 1 minus 2 z inverse. Okay. So this is the expression of xz we are having. Now first case, we will see mod z is greater than 2. You can see there are 2 poles. If you will see, there are 2 poles. One pole is at 1 pole at z equals to 2. Okay. and ROC is mod z greater than 2. It means we are discussing that ROC is here. Okay, ROC is here. The ROC we are having, this ROC means that the combined ROC is here. It means the ROC will be right sided or outward. Only then we are having this region obtained. Okay, so for mod z greater than 2, we are having right sided solution for us corresponding to both these poles. So the 1 upon 1 minus z inverse, you know, since a to the power n un is 1 upon 1 minus a z inverse. So here a equals to 1. So un will become 1 upon 1 minus z to the power minus 1. So you can see here minus 3 upon 1 minus z to the power minus 1. So when you will take the inverse z transform, it will become minus 3 un. And in second case, it is 3 times 1 upon 1 minus 2 z inverse. So 1 upon 1 minus a z inverse, and right sided solution, it means 3 into 2 to the power n un. Okay, so this is the first case. So this is the first case that we are having the result xn. Okay, in second case, we want ROC to be mod z less than 1. So mod z less than 1 means this is the z equals to 1, this is z equals to 2, and we want that our ROC will be here. ROC will be here. So it is only possible when ROC corresponding to pole z equals to 1 and z equals to 2 both is anti-causal. Okay, so we will write the anti-causal solution for this, and in case of anti-causal solution, you know, minus a to the power n u of minus n minus 1 is 1 upon 1 minus a z inverse. Okay, so corresponding to this, we are having the result of xn as 3 u of minus n minus n, 3 times u of minus, because minus sign will be compensated, and this is 3 of u of minus n minus 1, and here it will become minus 3 into 2 to the power n u of minus n minus 1. Okay, and last one is ROC is between 1 and 2. So this case ROC is between 1 and 2. It means you can see the ROC, this is 1, this is 2, and ROC 1 and 2, it means we are discussing about this region. Okay, so this region means when the ROC corresponding to z equals to 1 is outward and ROC due to z equals to 2 is inward, only then we are having this solution. So for first one, we will write the causal solution from here, and from this second one we are having anti-causal solution, which is this one. So this is how we are having the sequence xn in these three cases. Okay, now solving difference equation using unilateral jet transform. Unilateral jet transform is generally used for finding out the solution of differential equations. Okay, so we are having a differential equation, and with the help of that differential equation we can find out the solution. Okay, so if we will talk about the solution, then if we will talk about the response, so there are two types of response: zero input response and zero state response. So zero input response is calculated in the case when there is no input applied to the system, and the system output is considered based on the initial conditions of the system only. Okay, means we are assuming that only initial conditions are there and there is no input applied to the system. And second one is zero state response, means we are not assuming that there are any initial conditions, but the output that we are getting is due to the input only. Means the input, whatever input we have applied, we will get the output corresponding to that input only. Okay, so the total response of any system is zero input response plus zero state response. Zero input response because we are not applying any input to the system, that's why the response that we are getting is natural response. And zero state response means there is no initial conditions and the output is due to the input applied. So that's why we are calling it as forced response. So this is the one of the numerical based on this. So because of the time issues, I am not considering it. Okay, so these are the references. Okay, and thank you so much.